Okay, so let's try another dynamic scenario here, a little bit of forces. Let's see, let's just draw this. Here we go. Let's suppose we've got like a surface right there. Let's put, let's keep it nice and simple. Let's just get a box on here. There we go, let's get a little box. We can even shade it in. There we go. And we'll just have some guy pulling on the box. So, got some arms, legs. Apparently he's happy doing his work, something like that. And a little rope tied to it, something like this. There we go, and just pulling away. All right, let's try that. Okay, so let's say this is a 60 kilogram box. Okay, so a 60 kilogram box of whatever you want. And suppose it's already moving at 2.4 meters per second. And what he's going to do, he's going to pull. Okay, he's pulling the box. And he's going to go, let's say he goes 3 meters. And he actually reaches a different speed. We'll have him going faster, and let's say he reaches 5.6 meters per second. So that's actually pretty fast, but hey, it's all good. All right, so let's also have let's incorporate some friction with this as well. And let's say the coefficient of friction between the box and the ground is 0.35. All right, so we've got a 60 kilogram box with 0.35 coefficient of friction. He's starting at 2.4 meters per second. He pulls the box and reaches 5.6 meters per second after he goes 3 meters. Okay, so what we're going to do is we're going to find out how hard is he actually pulling the box, the applied force from the guy. All right, well, let's forget what we're looking for now. Let's just see what we've got. All right, so I got speeds and I got distance. I can work with that. I know he's starting at 2.4 meters per second and he's reaching 5.6 meters per second. So he's going from 2.4, I'm just going to map it out, he's going from 2.4 up to 5.6. Now, with that alone, I know acceleration is involved. And of course, acceleration likes to use a change in V. Average V also comes in handy. So I'm just going to find my V's so I can work with them. Change in V was 3.2. We went from 2.4 up to 5.6, which would be an increase of 3.2. And the average of the 2.4 and the 5.6, that would be just an even 4.0. Just add them up, divide by 2, an average V of 4 meters per second. Well, with that alone, I've got that average V. With distance and average V, I can find time. So I can do dTV, so distance over average V. So that would be the 3 meters divided by the 4. So 3 divided by 4 would give me a time of 0.75 seconds. This is one strong puller. Oh well. All right, now that I have time, what I can do with that, well, I've got time and I've got my change in V. And of course, with change in V and time, I can find acceleration. So my change in V was 3.2. My change in time was 0.75. I'll divide the two out and I get an acceleration of like 4.3 meters per second squared. So there's my acceleration. All right, now acceleration is awesome because I've got the mass as well. And with mass and acceleration, I can find net force. So net force would be mass times acceleration. Got the mass, got my acceleration. So I put the two together and I've got 256 newtons. So there's my net force. All right, now that's not my applied force because I got friction involved as well. So I want to try and find my friction. So I'm going to do that next. If I go over here, friction, of course, is mu Fn. And in this case, mu would just be equal to mg, just the weight of the box on the ground. So I've got my mu, I've got the 0.35. I'll times it by the 60 for the mass of the box, and then times that by 9.81 for gravity, and I'll plug and chug, and I get about 206 newtons of friction. And of course, since he's trying to pull it to the right, friction would be negative or going to the left, however you want to look at it. All right, so let's see if we can put things together. Well, he is pulling on the box. Now, the first thing that he would have to do in order to get this thing to move is he would need to take care of friction. Now, in order to take care of friction, he'd have to pull with 206. He needs to pull with 206 just to take care of friction. But he's doing more than that, because not only is he canceling out the 206 from friction, he's also winning with 256. That's why it's the net force. So to find out how much he's pulling with, I'm going to take those two forces and I am going to add them together. So his applied force must be the 256 and the 206 put together, which would give me about 462 newtons. So he's pulling with 462. He's losing 206 to friction, which then leaves him with the 256 as the net force. So he's got to be pulling with 462 newtons. Okay, all right, let's change the scenario a little bit. We'll take the same box, same guy. Let's just modify it a little bit. So, let's do a quick little sketchy redraw. All right, what if instead did pretty much the exact same thing, except instead of pulling straight to the side, what if he pulled at an angle instead? Suppose he pulled with the same 462 newtons, except now he's pulling at a 25-degree angle. Now this changes things a little bit. I'm just going to draw that 462 a little bigger down here, something like this. There you go. Now, when he's pulling with 462 newtons at 25 degrees, now he's sort of doing two things. He's not just pulling sideways, he's also pulling up. And this is where good old vectors kick in. He's pulling sideways, but he's also pulling up. This down here is often called force in the x direction, and this would be the force in the y direction, or vertical. Now it's just a right triangle, and what we can do is we can break it apart, use a cosine sine, use your basic trig, and figure out the sides of that little right triangle. And if I do that, I can find out that the force in the x direction, he's pulling with around 419 newtons sideways. And I'm also going to find the Fy. So I'm going to use sine theta for that one. And if I do that, he's pulling with about 195 newtons up. Now, these two forces do different things. The force in the x direction, this one actually, this is the one that actually causes the acceleration. That's how much force, that's the sideways force that's actually used to actually move the actual box. The 195, though, that's pulling up. Well, when he's pulling up against whatever's pulling down. Of course, gravity is what actually is pulling down. So as he pulls up on the box, this actually reduces like the pressure and the force between the box and the ground. This actually reduces the Fn. So by pulling up on the rope, he's actually reducing how much Fn there is. But Fn is directly connected to friction. So by lifting up, he will actually lower the amount of friction a little bit. Okay, so let's sort of see how this works out. Okay, so let's piece things together here. All right, so let's see how this affects the acceleration of the box. All right, now, if I want to look at how much is trying to move the box, well, how much is actually trying to move it? How much is actually trying to move from one place to another? Well, it's not the 462 because now he's pulling at an angle. It's actually the 419. That Fx, that 419 newtons, that is what's trying to move the box from one place to another. Okay, so that's fine. Well, how much is trying to slow it down? Well, that's where friction kicks in. But of course, friction is equal to mu Fn. Now, before, Fn was just the weight of the box, but Fn isn't just going to be the weight of the box anymore because he's also pulling up with 195. So if I wanted to find my new Fn, I can start with the mg. There's nothing wrong with that. I can just start with the weight of the box. That's fine. I'll do the 60 times 9.81. But then what I'm going to do is I'm going to subtract how much he's pulling up with. I'm going to subtract that 195 from it because he's reducing the normal force between the ground and the box itself. So if I do that, do the mg and I'll subtract the 195, we've got a normal force of around 394 newtons. So now I can find my friction. I'll take that 394 and I'll use that as my Fn. So I've got my coefficient of friction, that's still 0.35, I haven't changed that, times that by my 394, and I will get a force of friction of around 138 newtons. So you can see before, friction was 206. Now my friction's 138. I've got less friction because he's pulling up a little bit, lifting it off the surface a little bit, reducing the pressure, so we got less friction involved. Okay, now it's pretty much the same thing. How much is trying to move it? Well, 419 is trying to move it. Okay, that's what I have right here. 419 trying to move it. How much is trying to slow it down? 138. So I'm going to take those two together and I can find my net force. So my net force would be that 419 take away 138. So now I've got a net force of around 281 newtons. Once I've got my net force, I can find my acceleration. Of course, acceleration is net force divided by mass. So I'll take that 281, divide that by the mass of the box, which hasn't changed, and I get an acceleration of around 4.7 meters per second squared. So that's how you can take care of something like a wagon or a box, something being pulled at an angle. And the thing is, once you break apart that force 62, that initial applied force, once you break it apart into the Fx and Fy, you won't use it again. One of the most common mistakes I've seen students use in the past is when they'll break it apart, they'll do it fine, they'll find the friction fine, but then what will happen is right here, instead of using the 419, they would use the 462. No. Once you break apart that 462, you're not going to use it again. Fx is what's trying to move it, and the force of friction, which has been affected by the Fy, is going to slow it down. And that's about it.